Hello and welcome everybody. This is Soham, and today in this video we're going to cover about an interesting project that me and my team did at my college. And it's interesting because it covers about solving jigsaw puzzles. And why it is important? Because it has a lot of applications in self-supervised learning, learning latent representations for downstream tasks, or maybe in also contrastive learning. So we have tried out a bunch of different things in this project. That is different loss functions, different learning methods, different feature encoding methods, different decoding methods, and we have done a lot of literature review and also experimentation. This in this video, I'll try to go through everything, the presentation and the paper that we wrote. It'll also cover a little bit of the learnings that we had, and I'll try to go over each and every aspect of this project so that you could understand how did we do it, why did we do it, and the literature review that goes behind doing any project, any deep learning projects of sorts. Also about the neural networks or the approach that we took and why did we take that. So let's start. May up or Jigsaw. This is a dead neural network, and it can only be given life if you have a better loss function. So let's say, let's start the challenge, which is this. Let's say you have 10 seconds and this is a jigsaw puzzle in front of you, or you have to solve it in your head. You don't have anything. You can use a pen and pencil if you want. Yeah, done. So were you able to solve it? Take some more time. If yes, that's good for you. But if no, I'll tell you the answer. This is the answer. So do you feel that it is challenging to solve this in your head, or do you need to understand what is going on in the image? Do you need to understand what is the subject of the image? In this case, it was a horse. This particular image with a centerpiece was present here. There's this continuation between these two fences that led to having this particular images be in straight line. So there has to be a lot of back of the envelope calculations or reiteration or trial and error that you do in solving a jigsaw puzzle in your head. It is easy for you as a human because of a lot of different things, because of the capabilities that you have or the reasoning sense that you have. But for a model, it doesn't know what a horse is, first of all. Also, if you give this image and tell it to unjumble it, it will not be able to unless it is trained for that particular task. So it is difficult because for a human, you know that the horse's head comes after the horse's body, or the horse's legs come below the horse's body. Also, the tree is on top of the ground and ground is at the bottom and the sky is on the top. So you have some amount of domain knowledge that helps you in unscrambling this jigsaw puzzle or solving this jigsaw puzzle. So, and what you do is you take a piece, you try to, let's say you took this piece, you try to put it in this part, or you try to put it in this part. So you tried and you did a lot of trial and error to fix this piece in a particular part. You do this for each and every piece, and it takes a lot of time. So for a model which gives a direct output, how is it possible that you do it? So this is a challenging question. Also, let's say I have you a question about a binary classification, which is, let's say you have to predict, let's say given a object, is it red or blue? If I do it randomly, which is without using any model, I'll achieve an accuracy of 50%, because 50% of the times, let's say when my model pick about of 50 trials, 25 blue, 25 red, even if all of them are red or even if all of them are blue, 25 out of 50 times my model would be right. So it is 50% for a binary classification problem. But for a jigsaw problem, it is not as straightforward, because the probability of getting the jigsaw solved randomly is 1 upon 9 factorial, because you have 9 factorial permutations. In the previous image, if I go on, this particular piece has 9 different locations it can go to, which is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So for every piece, you have 9 different locations. So this has 8 different locations, 7, 6, 5. So that's why we have a 9 factorial total combinations of a single jigsaw puzzle. And if you divide that by 1, which is the actual image, it's around 0.00000027, which is very low. So if you are thinking that you could solve it randomly, there's no chance. So let's get into understanding the main crux of the problem itself. So what's the problem? So this complex problem solving tasks has many applications in computer vision, particularly in object reconstruction. So Gallagher in its paper in 2012, which I've cited down below, classified these puzzle tasks into three types, which is type 1, which is puzzle with translation without rotation, which we saw in the previous example where you just shift the puzzle and don't rotate it. The type 2, which is both translational and rotational, where you move the puzzle as well as rotate it. And type 3 is only rotation, so you rotate the puzzles in its own location. So we focus in our project particularly on solving puzzles of type 1 using deep learning methods. So let's talk about state of the art. So before I get into state of the art, it is time that we also start looking at the paper that we wrote, because I think I'll do the paper and the presentations in tandem. So it is easier for me to explain and you to understand as well. Yeah, so let's talk about the state of the art papers that have influenced a lot of work in this particular sector, which is solving jigsaw puzzles or reconstructing images, or solving jigsaw puzzles, learning representations for downstream tasks, learning latent embeddings for downstream tasks, for any similar problem. So the first paper that I will look at is by you et al. And the components of this paper that I have highlighted out there is the estimation of pairwise matching cost. So when it comes to a jigsaw piece, you have, let's say, two pieces. You have a piece 1 and piece 2. And let's say both of these pieces are your neighboring pieces. So what should actually happen is, if you try to look at it intuitively, is the gradient flow between the first image should be matching to the second image, or the differences between the boundaries should be minimal, because the image flows from one piece to another piece. So there has to be a boundary based or a pairwise similarity or pairwise boundary similarity between 2 or 3 pieces that are adjacent to each other. So let's say, for example, I take an image which is in the corner or the top left corner. The piece below it and the piece on right of it should be pairwise similar for this particular two boundaries, because those are adjacent boundaries and the gradient of the image flows accordingly and is similar. So it has used a linear programming based assembly strategy. Its fundamental contribution. And the advantages of being it is it's robust to incorrect pairwise matches. So it uses a linear programming based approach. If I get too deep into it, it's a different video itself. But this is the algorithm which I've pointed out here, which is, let's say you give input as a scrambled jigsaw puzzle piece. The output that you would expect is assembled image. So what you can do is generate initial pairwise matches and compute a certain matrix, and then you can go on in a loop until you have found a convergence, and then you can just trim and fill all as necessary to get the rectangular shape. So you can look at this paper and then dive deep into it. This is just a paper to get started. So the next paper is by Nuruzzi and Faro in 2017. The components of this paper are they built a Siamese type or Siamese and a network, which is a convolution network, and it has two different branches, where each row up to the first fully connected layer is a AlexNet architecture. So AlexNet is a old architecture you must be knowing. They use it for feature extraction, and they had used a shared weights mechanism. So they also decided to call it a context-free network, or CFN for short, because the data flow of each patch is explicitly separated until the fully connected layer and context is handled in the last fully connected layer. So let's say, for example, I'll just guide through it. Let's say we have this particular image of a car, and you have a permutation set for a particular index. Let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what it does is, in the context-free network, the figure illustrates how a puzzle is generated. they randomly crop a 225 or 225 pixel window from an image and divide it into a 3 cross 3 grid, which is the size of the puzzle they are aiming to solve. Even we are solving a 3 cross 3, a 9 type puzzle. What they do is they give this as independent parts to permuted parts to a fully connected network, or a network which has forward layers, which has A and N layers, and it has shared weights in between them, because all of these pieces are part of one single image. So let's say I have the original image, I permute it randomly and then feed it into a network. It extracts its features, it gets a representation, and in between, I share the weights of this representation that I've obtained per piece. So what the expected would happen is, after certain encoding and after learning some amount of representation for an image, if you share the representations that it has, let's say it has some representation learned, uh, when you try to classify each using a pointer network, or a network which is trying to classify each piece into a place or each piece into its original location, uh, then uh, you have shared weights. And then when you learn these shared weights and then back propagate, you learn representations, or representation in such a way that is able to classify all of these different permutations into a single right permutation, which is actually this permutation. So let's assume this to be our ground truth and this to be our permitted image, permitted tiles. You pass this into a network and expect it to classify, and then you can use those classes as the original image. You can also read in the in other transfer learning experiments. They have shown results with trained weight transferred on AlexNet. The training in the transfer learning experiment is same as in any other competing method. Notice instead that during the training on the puzzle task, we set the stride of the first year of CFN to be 2 instead of 4. So this is an important paper that has been well cited in the papers or the task related to jigsaws. This is also an interesting paper by Pomard et al. The components of these when the neural network predicts the position of the fragments. The graph that leads to the best reassembly is made from this prediction. So it uses a graph based and also information of the centerpiece to solve a given jigsaw puzzle, to reconstruct these images that it has mentioned in the paper. Let's say you have this image, it also has some amount of, let's say, eroded boundaries because it's not a well cropped 3 cross 3 for the entire image. You also have a sort of boundary mismatch because this is mainly done to reduce or to increase the complexity of the task, because the model may learn trivial things like the boundary flow, which was done in the linear programming or the LP based method. Like if you have, it would become trivial for the model to know that there has been a relationship between these two pieces, because that we can see a smooth gradient flow between these two. But since now we have broken eroded the image in between, the gradient flow is not that smooth, and the image looks more difficult to solve. The puzzle looks more difficult to solve. So the advantage is extended it to cases where external fragments and erosion. So, like I mentioned, it also tried to classify or solve pieces to which had external fragments in the initial puzzle set, or it also had eroded boundaries. So the paper's name is Deepzzle. So outline of the Deepzzle methods from a set of pieces A made up of central fragments. So this paper assumes that you have knowledge of the centerpiece, because let's say you have the knowledge of the centerpiece, it becomes relatively easier to understand what the other pieces are, because the for the example I gave in the beginning of the horse, if you would know the centerpiece, what the centerpiece was, it would become relatively easier for you as well to fix all the other pieces. So made a central fragment and lateral fragments. we pick a lateral fragment, which is any fragment apart from the center fragment. We extract its features and predict its place among the 8 lateral positions and the outside the class. So you have the 8 lateral positions remaining when you have the central class. Then they build a graph for prediction in which each line matches with a fragment. The reassembly E is computed from the shortest path in the graph. So this is how they try to solve this puzzle task. So if I will go into my paper and see the literature review or related works, there are a lot of literature reviews which match with this. This was achieved through methods aimed at characterizing and classifying the puzzle pieces, selection and rearrangement of pieces based on compatibility, determination of likelihood of fit, and finally by carefully evaluation of the puzzle assembly process. So this was a algorithm proposed by Freeman and Gardner. You also have the LP-based program which I discussed. There's also interesting work that had inspired us a lot in the project that we did, which was this particular paper. I'll show you the paper. It's by Lai et al. And it's an important paper because we have our work is mainly based on the on this particular paper, and we have drawn out different things from this particular paper. We learn about the implementation of a flow-based warp module that this paper proposes, and that we have also tried to use integrate in our networks to ensure correct alignment of the extracted features and image content from it. So this was a main output from this paper for us. So if you look at the network proposed by the particular authors of this paper, what they did was, let's say you have this inputs that you have, they separated, they divided the image into first 3x3 tiles, and then using maximal distance, which is, let's say, each piece is as far from its original location or no piece is in its correct location. So this is maximally deferred input to the model. So you have such setting where each piece is at a different location, no piece is at its own position. So this is your original input. So what they do is they have all of these inputs that they have, they put it into an encoder, let's say for encoding the representations or encoding the feature level parts. They extract the features. And then you have two branches that they diverge into, which is the classification branch and the generator branch. So what they do is they try to classify what type of image this particular input is of. So let's say this particular image FVC is of a house. So what they do is they try to classify what this image is of. So they use a jigsaw laws for this. Let's say the reference label being the house. You get a result for this particular input. Let's say this is a house. So for all general houses, the model has learned it tries to create a flow-based walk, which is, let's say, a house generally has these particular features, like let's say a door or a window or a chimney or has lights, and the door is usually at the bottom, the chimney is usually at the top, the windows are usually at the left or right or in the center. So this is a general image how the model has looked at for a particular house or particular set of houses, the images it is trained on. So it has understood that where certain features lie, where certain features don't lie. So this can be represented through the flow-based work for the 3x3 matrix. So for each piece, what we can do is you have a relative shift that you can do for a particular piece that brings it to the original location. This is a very important part because for a certain image, if you know the relative difference from its original location, what you could do is directly shift these pieces into its original location and then solve it to get the final output. So what they do is they generate this flow-based walk using the reference label they just generated, and then they go back and create this F warp. And they overlay this flow-based warp from on the warp that they have originally obtained. So when you have this with this, they put that into a residual block network, then they put it into a decoder block network, they reconstruct the image, And they reconstruct the image, they use two losses, which is the edge loss and the GAN loss. The edge loss is specifically so that, like I mentioned, the edges are smooth and the gradient flows smoothly in them. So this is captured by the edge loss so that correct pieces are aligned with its correct neighbors. And then there's GAN loss, which ensures that the image looks coherent and the image is actually a real house. So they backpropagate on two different branches, which is edge loss, GAN loss, and the jigsaw loss. So this is how backpropagation happens. And in the process, they learn the parameters of residual blocks, the decoder, the classification module, and the encoder. So this is so like I mentioned, our proposed novelty is we try to emphasize that the simple mode that a random reassembly chance for a 9-piece jigsaw puzzle solving is upper bounded by 1 upon 8 factorial over 9 factorial. It's very less and is also difficult for a normal human to try and solve the puzzle in one go. So our proposed methods, which are different from the original or the previous ideas that we have seen, is we assume no class label knowledge. So object detection or classification models can generalize more easily if they already recognize that the puzzle image depicts an animal. Unlike in the 11, which is the, let's say, the auxiliary GAN part or any Pomard et al., the paper by Pomard et al., our method does not rely on prior knowledge of the class label to which the puzzle belongs. So if I would have to give you an example of this, let's say we go back to the car example or the house example, where if the model already knows that the given shuffled image is of a car, what would happen is it would know that the wheels are usually at the bottom, the chassis or the body of the car is on top of it, and then the person, if there's a person sitting inside, is on top of that, and usually the ground is at the bottom or the sky is at top of the jigsaw image. So if you give the class label knowledge for the model in the model, the model would generalize more easily and it would find trivial solutions, which we don't want, because what we want is our model to actually learn and actually learn about the features or the representations that you have in the image. Second is iterative solving, which is instead of attempting to solve the entire puzzle at once, like in the previous papers that we saw, that you give an image and then you give an shuffled image as an input and it gives you a solved image as an output. So instead of attempting to solve the entire puzzle at once, our model iteratively adjusts the order and positions of the puzzle pieces step by step until convergence. So why is this important is because as a human also, you must have seen in the example that I give, is you try to look at each piece and then try to look at a particular place for it. You reiteratively do this again and again until you arrive at the proper solution. So we also try to do this and mimic this in our iterative solving model in our model. Second is we tried a lot of losses. So dead neural network and a proper well-defined loss is giving life to that. So we try and test a combination of multiple loss functions like cost cross entropy loss, boundary loss, Hungarian loss, reconstruction loss, scale divergence loss, and also a novel jigsaw flow loss. So we did not use all of these losses in one model. We used ensemble of some losses in some models, and we also have done an ablation study and tried to look at how each loss affects the model and what loss is well suited for a model. Also, unlike Pomard et al., we assume no centerpiece assumption. So, unlike some prior methods that assume knowledge of the center puzzle piece location, our approach does not require this prior information because it's like a guidance prior to the model, and it would again act at trivial because we want our model to learn the features and the representations. So, if it can solve the puzzle from an unordered state without central knowledge, it would be more beneficial or the model would be more robust in a sense. We also don't use any image and paint technologies because models like GANs or masked autoencoders or any fill encoders, we feel that it defeats the whole purpose of solving a jigsaw puzzle in general or learning, because if you have, let's say, a model or a jigsaw solver which solves 50% of the puzzle and you only have 50% of the puzzle left, which is model is not able to do that, we can directly use stable diffusion or GAN to fill the remaining image given reference of the individual pieces that we have. So this is not solving the puzzle, we feel. I may be wrong and you may correct me in this, but it's not solving the image, but it's like cheating and like getting your way through and just getting the output of the solved image. So we haven't used GANs, masked autoencoders, fill encoders, or any inventing methods to aid in the puzzle solving, because it defeats the whole purpose of learning raw available representations and then trying to solve the whole puzzle. So unlike all of these papers that I've cited, we don't use any diffusion or image generation models to learn similarities, but solve it with just the information of the shuffled pieces that are available. So let's get into some loss functions before we get into the dataset details and the actual model part. First is the cross entropy loss, our most favorite, or the daily loss in any classification problem. So to measure the dissimilarity between predicted tile position y cap and the ground truth y labels, promoting accurate classification by penalizing deviation from the correct label. So this is our normal cross entropy loss. The second important loss is the boundary loss, which looks something like this. So after a few experiments, we induced that using the cross entropy loss solely is very harsh for the model, because what would happen is, let's say, two pieces which are actually supposed to be together, our model gave them as together, but the original position is wrong. So let's say 0 and 1 are together, but they should go on 0 and 1. But my model gave my output as 0 and 1 were together, but they were in the position of 8 and 9. So the classification would directly say every piece is on wrong position, because 0 should go on 0, 1 should go on 1. But the model hasn't understood that our model has actually given 0 and 1 as together. So that's why we thought that the cross entropy loss solely is very harsh for the model. So to actually learn, since even if 2 or 3 pieces which are supposed to be together come together, our model penalizes that and forces a piece only be in the right position. So we devised to use this loss, which computes the structural similarity index, which SSIM for short, along the top, bottom, and left-right boundaries for each puzzle type. So for a given puzzle type, you calculate SSIM for each boundary that it has. The SSIM between two images, I1 and I2, which is like, let's say, tile 1 and tile 2, is given by this, where mu1, mu I1, or mu I2 are the means of image 1 and image 2 respectively. Sigma square sigma are the variances, and this is the covariances, and C1, C2 are the constants to stabilize the division with a weak denominator, so we don't get a very big loss or infinite loss. Next loss is Hungarian loss. So I'm spoiling you on the model a little bit in this, but after a few trials, we looked at the raw softmax output that we obtained, and we tried to solve the puzzle. We saw that the problem with the classification had assigns different puzzles pieced to a same position. So the one more problem with cross entropy loss is, let's say it's a centerpiece, 0, 1, 2, 3, 4. 4 is a centerpiece. 0, 1, 2, 3, 4. Yeah. So 4 is a centerpiece, and the centerpiece is at the center of the puzzle. So the model's calculation, or the probability that it would give 4 to be in a certain position will be much larger than any other piece, because it's a dominant piece. So what our model was doing is it was assigning 1, 2, 3, 4 to 1, 2, 3, 4, let's say, but 5 again to 4, 6 again to 4. But Jigsaw is a 1-to-1 problem. It's 1-to-1 onto problem. So each piece can only go to one place. 2 pieces cannot go to one single place. So this is why we use the Hungarian loss. Some papers have used things like pointer networks, which I'll be covering in a separate video, because it's a whole different topic that you have. Pointer networks, essentially, if I would give you a clue, is it solves combinatorial problems. So if you have 9 puzzle pieces as input, if you have permutation as input, and you want another permutation as an output for a certain task, it would only give you a certain permutation as an output. It would not give 2 things in one place. So this is where it is used. Combinatorial problems like traveling salesman problem or any such problem, pointer networks are generally used. So we did not use pointer networks, but we used the Hungarian loss to try to replace that. So since puzzle classification is a onto piece position task, the model should be penalized for assigning different tiles to the same position. Therefore, by considering all possible pairings of predicted and ground truth positions, the Hungarian loss ensures that the model learns the best matching strategy for solving jigsaw puzzles. So this was one loss. This one more loss that we used is the reconstruction loss, which measures the discrepancy between the original image and its reconstruction. So in the three different approaches that we have tried, one approach was using variational autoencoders. So this loss was particularly used in the variational autoencoder classification type approach that we did. Uh, the last is the Kullback-Leibler divergence loss. So you must have seen this particular equation to be common in models like dimensionality reduction models like a T-stochastic neighbor embeddings, where you have a high dimensional space and you try to reduce it to a low dimensional space, and you have to maintain the probability distributions in the high dimension to be same as the probability distribution that you have in the low dimension, so that the dimensionality reduction that you have done is accurate, correct. So there also in things like variational autoencoder, you have to measure to the similarities or dissimilarities between two probability distributions. So this is where the KL divergence or the KL loss is used, or the KL equation is used, where you have to see the differences between or the overlap between two distributions, probability distributions that you have. So if I would like to show you, this is how you could visualize the boundary loss for adjacent pieces. So for adjacent pieces, if you would look at this tile 1 and tile 2, which is actually adjacent, the neighboring tiles have a less boundary loss because they have more similar, less similar construction of pixels at edge. But at this particular point, you can see that there's no continuation between the images. There has been a gradient break between these two images. So like we talked about some methods using or exploiting this boundary condition that we have, which is the gradient flow, which Baum et al. Said that we will be eroding the images. So we did not erode the images. We have used the direct images. This is the where you can use the boundary and we can use calculate similarity and the gradient flow. So let's move on to the data details. So a data set that we have used for a preliminary classification or puzzle solving is the animals 10N data set. So it is a medium resolution with diverse array of classes and images like spider, butterfly, dog, squirrel, cavallo as in horse, etc. Yeah. So let's go on to custom data set creation. So let's say you have to segment images into a 3x3 grid of tiles to convert an image into a jigsaw puzzle at first. And then you can shuffle the tiles using maximal Hamming distance. So this was the Hamming distance I was trying to mention in the auxiliary GAN paper, where they try to see that every piece isn't in its correct location and is maximally distanced from the original location. So each piece is at a different location. No pieces are in its correct position, and you convert this into a 3x3 matrix and then just slice it. Yeah, so then we have the initial input for our model ready, which is the shuffled puzzle. Then we assign unique indices to the shuffled tiles that we have, and then we have developed 3 DL architectures for solving them to output a predicted sequence of tiles. So let's go back to thinking of first principles or basic puzzle solving task, which is you have a particular tile which we have to classify for a certain position, which is position 0, position 1, position 2, position 3, position 4. And for the correct reconstruction, the output sequence will be equal to the target sequence. So this is the target, which is the position 0 should be on position 0, position 5 should be on position 5. So this is a shuffled image and this is the target. So each tile is getting classified into its correct position, or let's say a correct class, and a class is the correct position. This is a basic classification task. So let's think of first principles. What's the first model that comes to our mind when we think of extracting features and then doing a classification problem on top of that? So to assign a baseline, we go here, which is a baseline convolution neural network ANN model. So
Let's say you have this image passing a stitched image. So when you have this particular image, what we'll do is our model will give you our model will extract each particular piece from this. We'll use convolution. We'll do convolution. Then we'll do max pooling. At this particular stage, we have the feature per tile ready, and we have 9 such features or 9 such vectors that will go into a fully connected activation function, which is a artificial neural network, and the output of this being softmax probabilities, or the output being classification probabilities of each particular tile vector or each particular tile that you have into a correct position. So you extract the features and then you do classification on top of it. So you go essentially at the output, which is classifying each tile into its correct position. This is the baseline convolutional neural network ANN approach that we did to just establish that is it possible that a bare bone model is able to solve a task which people have been struggling for a lot of years. So the baseline accuracy that we actually obtained was 18. So 18 is per piece accuracy on the test set that we have, which is actually very less. And it's evident because we have used a normal cross entropy loss, like I mentioned, is not suitable because it's a very harsh loss and is not able to capture everything that we are trying our model should learn. And also just using convolutions and just using a basic 3-4 layer ANN is not enough for doing classification, because the model hasn't ever been able to learn the internal representation, and nor the model has knowledge of the label or the class of the shuffled image. So the baseline accuracy is 18. So we updated the CNN ANN model. So passing the stacked tiles, like I mentioned, you have the input image, you have the stacked tiles as 9 different vectors that you have, which is each piece is one vector, let's say one matrix. You pass that into convolution 2D, each tile, each image into convolution 2D for every single piece. Then you do max pooling plus batch normalization. Batch normalization is ensured to that we could reduce the internal covariate shift that we have in the models. Then you have the fully connected ANN networks like previous model, and then you have the output. And in this, we have used max pooling plus batch normalization and then normal classification. So the accuracy increased in this because I have not mentioned the losses that we used here, but we also started using a different bunch of losses for this particular baseline accuracy. So the accuracy jumped from 18 to 35, 38 because we have tried using a different losses and also the reiteration approach. So the proposed approaches are CNN, ENN plus reiteration, which is this. By reiteration, if I want to explain you what does reiteration mean, is let's say your model gives output of raw logits that you have, and you pick the strongest piece, the piece which has the largest probability from all of the pieces. Let's say piece 0 being at 0 has the highest probability in all of the different matrices that you have. So the output would be a 9x9 matrix. Each column, let's say, represents for piece 1, which is the most probable location. And for every piece, we have 9 such columns, because for each piece, we have 9 such options. So it's a 9x9 matrix. So what we'll do is we'll pick the maximum value in it. We'll assign that puzzle piece to that particular place, and then we'll mask out that particular column. So because that piece is already filled, then you have remaining 8 pieces. When you rerun the model, and when you rerun the model, then you have to classify out of 8, because in 9 you have minus infinities, let's say. It classifies the type which is fixed, but you mask it with, let's say, minus infinity. And then you pick the next highest probability piece. You fix that. You do this iteratively. So what you're doing is essentially arranging each piece in a descending order. Descending by descending, I mean the highest probability piece goes to its right position. Then you assign the second highest probability piece to its position. Do this for every piece, and that's why the accuracy in this increases to 35-38%. So take a moment to absorb what I just said, and please, if you have any questions, let me know. Yeah. So last time we left at this particular slide, and I've told you to absorb what did I speak till now, which was regarding the approaches that we have covered till now, which was the updated CNN ANN model, and the accuracy that we have got here per piece accuracy, which is 35-38%. So let's move further, and then using the baseline that we had, we proposed 4 different approaches, which are a CNN ANN plus reiteration, which I have spoiled you a little bit on. The second is GNN, which is a graph neural networks, which is classification and edge prediction on top of that. Third is a technique that gave us our most good result, which was using flow warp technique, and it was a technique inspired using the Lai et al. Paper that I showed you in the architecture that I showed you. And the last that we tried was regarding using variational autoencoders for classification. So VAE is actually used for generating images, if you could think of that. But I had some experimentations in my mind, and that's why we and my team we experimented on using VAE for classification. So let's move further, and I'll now start talking about the implementation and the experimentation. And the lessons that we learned on the way using all of these approaches and the loss functions and everything else. So there are a number of problems when it comes to solving jigsaws using DL. What we thought of was you have no information of piece orientations, because that is what makes a puzzle a jigsaw puzzle, and then you have to solve it. Second is no information about the class labels. Like I mentioned, if you have know the class labels, it would become trivial for the model to know that if it's a car, then the wheels would go on the bottom and the chassis would go on the top. Next is less compute for generation. Also, since we are students and we have limited compute, which is Google Colab 34 GPU, if we use independent technologies and train our model, so it defeats the whole purpose of representation learning, as well as a lot of compute is needed to train any generative adversarial network or any independent technology of sorts. So also, when it comes to time complexity, you cannot solve half of the puzzle and then use a brute force to solve a jigsaw puzzle, because there are like 9 factorial different ways to jumble 3x3 piece or a puzzle. So we try to replicate the human nature within our models, and we call it the trial and error, the reiterative approach, which I have spoken in the previous part. So if you could look at this, the updated CNN ANN model with the reiteration, where you have the pieces here, then you put them through convolution, then you max pool them. Then you have the artificial neural network, which is fully connected layers with activation functions. And then you get the probabilities out, and then using the maximum probability scores, we find out what part goes where, and we do that iteratively, and we in the end get all the probabilities, and then we maximum probabilities and all the class labels, and then we reconstruct the image, and then we get our original image or the solid jigsaw puzzle. So using this, we got our most highest accuracy, which is 44.95%. This was very good, since we try to replicate something which we hadn't tried earlier, which is the reiterative classification approach. So you can also try this using, you can also use this in your data imbalance, is what I've tried experimenting in. Let's say you have a 20% of minority class, 80% of the majority class. Then, and if you have a domain knowledge that for a given classification problem, out of 100 entries of, let's say, 20% will be a minority class, they will be present for sure. So you can then first classify these 20 entries using the maximum probability, and then you can directly use remaining for classification of if it's coming from majority class or the minority class. So you can use this technique in your projects if you like that.
Yeah, so this loss I talked about is the Hungarian loss, because our model can possibly assign multiple tiles to same position using the cross entropy, but which one should be assigned finally? But one position can only have one tile, so cross entropy loss spans across all indices. So we use this loss to solve the assignment problem. Some people also use pointer networks, but that is a different topic. Then we come to the graph neural networks baseline. So on the left side, you may see a jumbled image, and these are the pieces. So it's also image of a horse and a person riding the horse. So if you would think that, let's say, we can use one tile or one piece as our one node in one graph, and then the connections that the graph makes is basically the solved jigsaw puzzle. So for this particular piece as a node, it would be connected to this part, and this part. Similarly, for the center piece, it would have the most adjacent pieces, or it would be connected to all these different parts if you are keeping the diagonal edges as well. Otherwise, it would be just connected to these four pieces if you're not keeping the diagonal edges. So you can convert this into a graph, and then you can also look at this as a graph problem where you are trying to predict which edges exists and which edges do not exist. So for this particular piece, if these two are not adjacent pieces, which are not, then edge should not exist between these two nodes or these two pieces that you have here. This should be actually connected to its original piece. So but the problem, we tried training it on this, but the problem is when you do graph neural networks, I'll give you an idea is there's this message passing or information transfer that happens between two nodes. So if you have two pieces which are not adjacent, and they're actually being in your jigsaw puzzle as adjacent pieces, so during GNN training, what would happen is it would pollute the information, because the GNN doesn't know what part is where. We are just trying to do this resulting prediction problem. So this is a problem that we faced using GNN. We also tried using a GCN. So if you go in the previous slide, you have to use each image, extract its features, and then put it into a node, and then use that node as a feature vector for a particular tile or a particular image. And then you can do link prediction on top of that. And you can also use GCN. There are videos coming up about GNN and GCN also on internet, but when we solved this problem, there were a very limited resources. That's why it also became difficult for us to constantly follow through what we were trying to do and how are we going to do it. So if I would want to give you a basic idea about how did we tackle this, is let's say you have this input that you have. We trained our model to know what actually a good solved jigsaw puzzle looks like. And then when we give an input image or an input graph, it should formulate it in such a way that it matches the overall structure, overall idea of that particular image. So let's say for an image that belongs to horse, the structure of the graph should look something like ABC, let's say. When you bring in the shuffled image, it would look like BCA. So we have to transform BCA to ABC so that the shuffled image looks like the original image. So if you can think of this, you can also think of this in that way. If I look at this, what we did is we segregated our image into 9 pieces, which is our 9 puzzle pieces. And also we divided each piece into 4 different parts. So this is done so that we get more granular information and we can see adjacent links and internal links. So the internal links in this image are denoted by the purple color. So these two between a same single piece is the internal link, whereas this particular piece, if it's connected to the adjacent piece, this particular link will be called as an inter-piece link or an adjacent link. So this is how it looks like. You can watch it here and or also absorb this particular slide in. So what we can do is we have the graph data, then you have the graph adjacent data. I'll tell you in a minute what graph data and graph adjacent data means.
And then you add a negative samples because you also want your model to learn what edges exists and what edges do not exist. So that is done by ensuring negative samples that you have in your graph, and then you can add this and directly pass it into, let's say, ANN to do your classification for you. So negative sampling is carried out on graph adjacent data which has adjacent links. Adjacent links, I mean by the enter green links between pieces. And the graph data uses all the internal links, which are the purple links. We then concat both of the graph and ensure that the training data include all edges except those specifically filtered out or removed. So model learns to identify and predict missing edges presence. You can also look at this. There's an input graph. You pass it into an encoder. It convolutes. It uses graph convolutions. Then you have the node embeddings for each node. What you can do is also add negative links. Then you have this particular graph ready. And then you can pass the node embeddings that you have from the graph convolutions output and the negative embeddings and decoder network, which uses a node pair multiplication and aggregate embedded dimensions. And then using this decoder, you have a sigmoid output, which gives you the output that you have, which is, let's say, the solved jigsaw piece or the nodes which should be connected to each other, and the actual links between nodes and the pieces that you have. Yeah, so before the flow method, let's see what we have covered till now and how did our model outputs looked when we tried to reconstruct the image using cross entropy loss and other losses. So this is the original image and this is the target sequence. That's the correct solved puzzle. And then using cross entropy loss, the model gave out this particular output, which looks exactly the same as the original and is not able to solve. So in this, it was able to solve some amount of parts. Let's say that this leg part, this body part, this tail part, and other pieces are not at all in its original location. So in the graph neural network approach, I just summarize that each node represented a sub-piece in the puzzle. The primary goal here is to ascertain where a link should exist between adjacent nodes, and we train a link prediction model on unjumbled images to forecast connections between the pieces. The processing of each image involved dividing into 3x3 grid, which we always do, and which are 9 larger blocks, and each block is then subdivided into 4x4, which leads us to our graph adjacent data and the graph data. So I'll tell you the teachings and the learnings that we came out of using this and how did we discard this particular model, although it was looking promising in the first part of our project. So several factors led to our decision to move away from this approach. Firstly, there are limited resources available on the internet regarding link prediction applied to images, which posed a significant challenge. Additionally, the structure of the input data required a thorough understanding that our input should be a graph, where each subgraph is connected to all other and each represents an image. So, however, there was uncertainty in how to process the data effectively within this framework. This complexity in data handling and the lack of support resources were key reasons to abandon this method. So keep this in mind if you're tackling a similar problem or you're working with GCN or GNN. I'll just cover a variational autoencoders approach in a minute or so, because this approach we tried, but I think if I would want to include this approach as well, this video would become very big, because VAE is a separate giant topic in its own way. But if I want to show you visualize some things like how the graph visualization looked like when you have the internal edges, which are represented by the blue color, and the adjacent piece edges, which are represented by the red color. So this is how the graph looks like, graph with internal and adjacent edges. So there's so many graphs, so many links that you have, and you have to predict the adjacent edges using the internal edges and the information. So if we want to look at the variational autoencoder classification problem, what you can do is let's take this image for now, because I'll show you what the VAE looks like. So it has an encoder module. It does something special in the middle, which is sampling from a distribution, and that's a decoder module, and it reconstructs a given image. So let's say you have an image of one celebrity. It encodes it. It has some representation down here. and it decodes it and then creates the face or anything that has the celebrity. But if you see the outputs of a VAE decoder, how it looks like is the celebrity's background is usually getting blurred. The face has some amount of clarity to it. So it also uses this trick called as reparameterization trick, because in this particular part where you're sampling out of a distribution, sampling is not differentiable, because if you're calculating loss at this particular end, the backpropagation should only stop here, because before this you're sampling some points. Sampling is random sampling. So how do you backpropagate to this and go to encoder layer where the model should learn how to extract meaningful features? So there is a big topic which we could cover later. So it has and this is how a VAE looks like, with an encoder, decoder, and a sampling technique in between. So we did the same in this, and let's say you convolute it and you have some representation. You deconvolute it and then you have some representation, and then what you can do is, using the representation learned, what you can do is directly classify, because then this VAE has learned a representation of each particular piece or each particular image. And then using the information or the encoder learned information or representation, what we can do is put out an just ANN, which classifies the learned representations into particular classes, which we can use to reconstruct images. So yeah, so this is the VAE approach that we have. Let's go to the flow warp method that we have, which is the kind of encoder decoder technique. And we have also used a segmentation type of approach in the flow warp method. Let's go. So since I've been talking a lot about losses this video, so it's all about the loss, and what kind of approach that you take and what kind of optimization that you're trying to do, or what are the things that you're trying to maximize. So what we did is a provision of general direction of movement and like preset classification. So let's say you have an shuffled image. Each piece is displaced from its original location. So let's say this piece should go here. So this piece should go one step down. So in the vertical displacement part, you can see there is one step displacement here. This piece should not get horizontally displaced because this is the centerpiece. So you may see this as a square, or let's represent it as 0. So each piece is displaced from its original location. So you have an horizontal displacement and a vertical displacement for each piece. So for each shuffled image, you have a flow wrap or a flow warp that you have, which is two particular regressed matrices which denote how much is a piece away from its original location. So if you have this particular information along with your convolution neural network, which extracts features, I think this would be able to solve the puzzle. So we also use gradient flow loss, which is neighboring. So let's see, these two are neighboring pieces. So there has to be a smooth gradient flow, which I have been talking about. And also it should, if the pieces are non-neighboring, the gradient should be strict, like it should not be able to pass freely. So this is the gradient flow loss, and you can see visualize it for two adjacent pieces and two non-adjacent pieces. We have also tried of using segmentation, which is what we do is for original image we segment it. So this ensures that you have a shape outlined for a particular image. So we use a unit model to do this, but the main principle behind using a segmentation was we have to also highlight the shape of the subject in the image. So sometimes what would happen is the image is not of a particular subject, but if you have segmented parts in an image, you have clearly defined boundaries, which are sometimes not easy to catch, although you have the vertical and the horizontal filters. So we also aid the model and give it a segmented image or segmented flow map of the image, so that it could see the shape and learn from it. So the unit model is so good that it also performed well on the segmented shuffle part, because the main question to you would be, if I shuffle the image and then segment it, is it able to preserve the performance that it has? But UNet was able to do that, and surprisingly well. So you may see it has a good segmentation even for the shuffled image. So if you just look at this, if I just hide this particular left image and just look at this, you may be able to see that this looks like legs. This is a face, so this should come here, this should go here, this should go here, this should go here. So you also get an idea from the shuffled image as well. So this is what we thought that could also aid the model like it aids humans. And the gradient loss on segmentation is also great, because there's very harsh gradient flow when you look at these two segmented images, which is not the case if it's here. So if it gets divided in this particular part, the gradient flow is smoother here, smoother here, smoother here, smoother here. So which is not the case if you have this particular image. So this is the final flow warp model that me and my team, along with my instructors, teacher assistants, we came up with. Take a minute to digest this, because it's a simple architecture. It's not that difficult. We are doing the same thing like what we did in our previous approaches. It's just the images that we have. We convolve them. We do batch normalization so that there's no internal covariate shift, because these images come from a lot of different animals, because we're using the animal talent dataset. Then we do max pooling. Then you have the ANN network that you have. Then you have the flow warp model that we have, flow wrap model that we have, which shows the horizontal displacement and the vertical displacement, which gives the horizontal and vertical displacement. Because if you look at this becomes a regression type problem, because each piece can go either one place down, two places down, or one piece right, two pieces right. So this becomes a regression problem. And then you pass these pieces into a pre-trained segmentation model. Then you convolute it, batch norm, convolute, and then you have a segmented feature set ready here. You have the flow map ready at this point. You can concatenate these features for each piece, because for each piece you have a feature ready, segmented feature ready, and then you have the displacement for each piece ready. If you use both of them and pass them to an ANN, the ANN could give you an output of the each particular position. So this is how the final flow warp model looks like. You can also, you can also use the trial and error approach in this particular part, or in this particular part, where the model gives out the cross entropy logits or the probability scores, and then you can fix the maximum piece, then you can fix the second maximum piece, and so on to get the output. And yes, we were not able to fully train this model, because since I'll tell you one problem with this is, since you're using pre-trained segmentation model, the data loaders that we had formed were very big, because we had a lot of images in our training loop, and for each image we had to have a segmented a subpart ready for that particular image. So the data loaders were becoming too heavy, and since it's a pre-trained model, so the back propagation that occurs does not go through this particular part. It only goes through this particular part. So since the batch loaders or data loaders were becoming too big, and also we had a lot of images, it was becoming difficult to train this entire model in one go on the T4 GPU that we have, collab that we have. So the only thing that we were able to verify is that our model showed 60% validation accuracy. So I think this model shows a promising result using the segmented flow warp and the displacements that we have, and using the cross entropy loss. Yeah, so let's go on to the results and limitations. I think the results, I'll talk in the slides as well. Yeah. So There's some limitations when it comes to results and solving jigsaw puzzles. So sometimes only one piece is different from the original piece. So our model gave this as an output, this as an output, this as an output. So, but if you look at it carefully, these two pieces are wrong. These two pieces are wrong. These two pieces are wrong. But for a person, if you put this piece here, the puzzle is solved. So that means only one piece is out of its original location if you think of it that way. But for a model, for cross entropy loss, this is two different pieces are wrong. So it directly drops to 7 upon 9. Sometimes it is visually correct. Sometimes the images are visually correct, but the model gives them as wrong outputs because you have the original image with the target sequence and you have the predicted sequence. These two images, these two tiles are wrongly placed, but since both of them are entirely white in color, it's difficult for a human as well as model to distinguish between these two tiles. So the target sequence and the predicted sequence visually looks good, but the classification accuracy goes down. And some people, some papers have taken this to be at 100 accuracy per piece because it's visually correct. We did not do that. So that's why our accuracy scores are below a certain threshold. So the accuracy is defined by per piece accuracy. So it's number of correct pieces divided by total number of pieces. So if you have a total of 9 pieces and 2 of them are incorrect, 7 pieces are correct. The accuracy will be calculated as 7 by 9. So it drops to 77% directly. So the accuracy game is very tricky in jigsaw solving business. So these are the results from different experimentations across the models and the losses that we have, which is the CNN model, this CNN GCNANN model, the VAEANN model. You can look at this, and we have not added the flow warp method, the 60% validation accuracy, but it is mentioned in the slides. Have a look at this and then let me know if you have any doubts. With reiterative solver, by this we mean the trial and error approach that we have mentioned. If we look at comparative analysis using SOTA, you have the vision transformer. There you have also have a Jigsaw VIP. You also have GANs. You have the CFN network that I have mentioned in my literature review, and it has a piecewise accuracy. But some of these models were not entirely made to solve jigsaw puzzles. They were made in such a way that they could be used to learn representations and be used to solve more downstream tasks such as normal classification problems or normal any image self-supervised or training problems. So this is where we fit in if we don't take the flow walk method, which is 60% validation accuracy. But I think it's less, but because of the results and the issues and the tricky business that you have in taking the piecewise accuracy in Jigsaw, I don't think this is representative of the work that me and my team did, because since you have seen a lot of approaches and a lot of different techniques that we tried. So yeah, thank you. We assure originality, and let me know if you have any questions. I'll just go through the last pages of the paper, which is a flow warp technique that we have here. It's same that what I mentioned. It's just written more comprehensively in this particular paper, and you have the results and the conclusion being the project introduced several novel algorithms and architectures for assembling square jigsaw puzzles of size 3x3, operating under constraints of limited computational resources, like I mentioned, the data loaders. We explored the efficacy of hybrid algorithms and various loss functions in solving jigsaw puzzles, highlighting versatility and adaptability of deep learning techniques in handling the complexities of puzzle reconstruction. So lastly, all code for this project we had developed from scratch with no reliance on the pre-trained models except in the case of image segmentation. So yeah, thank you. And if you have any questions, please let me know.